if the distance between the plane ax minus 2y plus z equals d, and the plane containing the lines, and they give us two lines here in 3 dimensions, if that distance is square root of 6, then the absolute value of d is. So let's think about it a little bit. They're talking about the distance between this plane and some plane that contains these two lines. So in order to talk realistically about distances between planes, those planes will have to be parallel, because if they're not parallel, if they intersect with each other, the distance is clearly 0. And they're telling us here that the distance is the square root of 6. So we have a situation so that the planes can't intersect, they must be parallel. So you have this plane up here, you have this plane up here. We could call this, the equation here is ax minus 2y plus z is equal to d. And then you're going to have another plane that's going to be parallel to it. Maybe it looks something like this. You have the other plane that is parallel, and it's going to contain both of these lines. So maybe it has this line. So this line is in, I'll say it in green. Maybe this line looks something like this. It's on that blue plane. And then this line, maybe in magenta, is also going to be on the blue plane. So how can we figure out the distances? Well, a good starting point would be to try to figure out the equation for this blue plane here. And since these planes are parallel, this equation should look very much like this orange equation, at least on the left-hand side. It might just have a different d value, and that's because it has the exact same inclination. And then once we figure out the equation for this plane over here, then we could actually probably figure out what a is. Then we could find some point. On the blue plane, and then use our knowledge of finding the distance between points and planes to figure out the actual distance from any point to this orange plane. So let's figure out the equation of this blue plane first. And a good place to start is just to try to figure out two vectors on this blue plane. Then we can take the cross product of those two vectors to find out a normal to the blue plane, and then use that information to actually figure out the equation for the blue plane. So let's figure out first some points that sit on the blue plane. So on this green line right over here, you have, see, if I want all of these to be equal to 0, you'd have the point x is equal to 1, y is equal to 2, z is equal to 3. So you'd have the point 1, 1, 2, 3. That definitely sits on the blue plane. Let's come up with another point. Let's see, if I want all of these to be equal to 1, I could make this, if I want this to evaluate to 2, I would have the point 3. I would have the point, if I want this to evaluate to 1, I would want 5 minus 2 over 3. So 3, 5. And then I would want this to be 7. 7 minus 3 over 4 is also 1. So that's another point. Actually, both of these points sit on this line right over here. 1, 2, 3, and then 3, 5, and 7. And then let's do the same thing for this. Let's find 2 points on this plane. Actually, we just have to find 1 point on this plane, because if you have 3 points, that's enough to figure out two different vectors that aren't scalar multiples of each other, which would be enough to figure out the normal to this plane. So let's just figure out one more point over here. And one more point would be, if we want all of these 3 to be equal to 0, would be the point 2, 3, 4. 2, 2, 3, 4. Because this would be 0, 0, 0. So that's also sitting on the plane, and that sits on the magenta line right over there. So let's use these 3 points to figure out two vectors on the plane that aren't multiples of each other. Then we could take their cross product to actually figure out a normal vector to the blue plane. So let's say the first vector, a, that sits on this plane, let's say it's the difference in the position vectors that specify these 2 points. And we know that'll be on the plane. And so that will be 3 minus 1 is 2i, plus 5 minus 2 is 3j, plus 7 minus 3 is 4k. So vector A is actually going to be is actually going to sit on this green line because both of these points are on this line. So it's going to sit on that line. If we put it on the plane, or if we were to start it at one of those points, it'll sit on that line. And then we could do another vector. And it's essentially going between a point on the green line and a point on the purple line. But that's definitely going to be a vector on our blue plane. And let's go between these 2 points. That looks pretty straightforward. So let's call vector B. Let me do another color so we don't confuse ourselves with that purple. Let's call vector B. Let's call that, let's see, 2 minus 1 is I, 3 minus 2 is J, and then 4 minus 3, that's just 1K. So this vector right here is also sitting on the plane. So if I take the cross product of A and B, I am going to get a vector that is perpendicular to the plane, or a normal vector to the plane. So let's do that. So let's find what A cross B is. A cross B is equal to, and this is how I find it easiest, I just write I, J, K. This is really the definition of the cross product, or I guess one of them. And we write our first vector. We have 2, 3, 4, and then we have our second vector, which is just 1, 1, 1. And then this is going to be equal to, first we'll look at the I component, so cross that row, that column out. 3 times 1 minus 1 times 4. So that's just 3 minus 4. So it's negative I. And then minus, we're going to have the J. So let me write a minus here. Minus, we just swap signs. We have positive, negative, positive. So J, get rid of that column, that row. 2 times 1, which is 2, minus 1 times 4. So that's minus 4 is negative 2. So we could write a negative 2 here, but the negatives cancel out. So it becomes plus 2J. And then finally for the K, get rid of that row, that column. 2 times 1 is 2, minus 1 times 3 is 2 minus 3, which is negative 1. So it's negative K. So this right here is a normal vector. This right here is a normal vector, to the plane. So if we want to find the equation for that plane, we've done it multiple times. We just have to take the dot product of that normal vector. We just have to take the dot product of that normal vector and any arbitrary vector on that's specified, that we can specify with an arbitrary x, y, and z. And we've done this multiple times in multiple videos. If this is any point x, y, z that sits on the plane, so this is any point x, y, z that sits on a plane, then the vector, let me draw the vector. Let's say we go to this point right over here. So this vector right over here is going to be, let me draw it the other way actually. So this vector right over here, let's say we're going between this point and x, y, z. This vector right here is going to be x minus 3I plus y minus 5j plus z minus 7k. That's what this vector is. It sits on the plane, assuming x, y, and z sit on the plane. So if we take the dot product of this and the normal vector, that has got to be equal to 0 because it sits on the plane, and then we'll have our equation. So let's take n dot that over there. So n dot x minus 3I plus y minus 5j plus z minus 7k. And if any of this is confusing to you, I've gone into a little bit more depth in previous videos, especially in the linear algebra playlist, where I talk about constructing the equation of a plane given a point on the plane and the normal vector, and even how do you find that normal vector. So you might want to watch those if you want some review there. But these are going to be equal to 0. So when you take the dot product, and our normal vector is this. So we just take the x term, which is negative 1, times this x term right over here. So negative 1 times this is just 3 minus x. And then plus this y component times this y component. So it's 2 times this. So it's plus 2y minus 10. And then finally, the z component, negative 1 times this. So this is plus 7. Plus 7 minus z is equal to 0. And what do we get? So we have our negative x plus 2y minus z, and then is equal to, let's subtract 3 from both sides. So if we take it out there, it'll be minus 3. If we add 10 to both sides, so then you have a plus 10 over here. And then we subtract 7 from both sides. This becomes a minus 7. So then on the right-hand side, negative 3 plus 10 minus 7, well, that's just going to be 0. That's just going to be 0. And just like that, we have the equation for this blue plane over here, the plane that contains these two lines. Now remember what we said at the beginning of the video. These two planes are parallel. So the ratio of the coefficients on the x terms, the y term, and the z term has got to be the same. And so this one has a positive 2, that has a negative 2. This is just to simplify it so it looks very similar to each other. Let's multiply this equation right here, both sides, by negative 1. And then we're going to get x minus 2y plus z is equal to 0. So this is a completely valid, another alternate way of expressing this same plane. And what I like about this is it looks very similar to this, at least the ratios of the x, y's, and z's. Negative 2y, negative 2y. 1z, 1z. And remember, the ratios have to be the same. So here we have a 1-to-1 ratio between the z coefficient, the z coefficient, the y coefficient, and the y coefficient. So it's also going to be for the x coefficient. So here we know if this is going to be parallel to the blue plane, we know that a has got to be equal to 1. So this is x minus 2y plus z is equal to d. So now let's figure out the actual distance. Let's actually figure out the actual distance between these two planes. So what we can do is we can take a point on this blue plane, and we have several examples of points on the blue plane, and find the distance between that point and this plane over here. And actually, I just finished doing some videos on how do you find the distance between a point and a plane. So I'm just going to use that formula. If you want it to be proved, go watch that video. It's actually a pretty interesting proof, I think. But the distance between, let's say, this point, 1, 2, 3, and this plane over here, and this plane. So this distance right here is going to be in the direction of the normal. The distance is going to be, and I want to be careful not using that. So I'll actually write out the word. Don't want to overload variables. The distance is going to be, you literally just evaluate this. Let me do it this way. You literally put in this point for the x, y, and z, and then you subtract the d in the numerator. And we saw that as the formula for finding the distance. So it's literally going to be 1. I'm actually using this point right over here. It's going to be 1, because we just have 1x, so it's just going to be 1 minus 2 times 2. 1 minus 4, that's 2 times 2, plus 3, minus d. Well, here, the d is just d, so we're just going to write minus d, just like that. All of that over what is essentially the magnitude of the normal vector, and we saw in several videos, that's just the square of the coefficients on each of these terms right here, and taking the sum of those, taking the square root. So it's going to be equal to 1 squared plus negative 2 squared, which is 4, plus 1 squared, which is 1. So this is going to simplify to the distance is equal to 1 minus 4 plus 3 is 0. So in the numerator we have negative d, all of that over the square root of 1 plus 4 plus 1. So all over the square root of 6. So they say the distance, if the distance between the plane ax minus 2y plus z is equal, between this plane and this plane over here, is square root of 6. So they're saying the distance is equal to the square root of 6. That's what this information right over here is. Maybe I should do that in another color. So this distance right, that's not another color. The distance between the two planes is going to be the square root of 6. And so then if we solve for d, multiply both sides of this equation times the square root of 6, you get 6 is equal to negative d, or d is equal to negative 6. Now, what they care about is the absolute value of d, or the absolute distance. And that's actually, this would be kind of the signed distance. It kind of specifies whether we're above or below the plane. Since we're below the plane, we got a negative number. I just happened to draw it right. If we were above the plane, we would get a positive number. So this distance is negative 6, the absolute value of it. The absolute value of d, which is the same thing as the absolute value of negative 6, is equal to 6. So take any point on this blue plane, and you look for the closest point on the orange plane, and they will be they will be exactly 6 apart. Anyway, hopefully you found that interesting.